Hello and welcome to Lapping Analytics. My name is Jimmy Lapping. I'm a psychologist and statistician with an interest in statistical methods for social and health sciences and in AI applications in this context as well. And in this video, I show an example of how to perform non-parametric statistics using ChatGPT. I mean, I'm using the free version of ChatGPT, but you could also do this in some other programs, such as, for instance, DeepSeek, where I've tried this as well. In a recent video, I showed that it is important to carefully formulate your questions when you're trying to do statistics in programs like ChatGPT. I showed how it is possible, for instance, otherwise for ChatGPT to provide incorrect outcomes. So it's really important to make your prompts as specific as possible. So what I'm going to show here is directly from the free version of ChatGPT. Basically a two-group comparison. So we have values for the control group, which we see here. We have a total number of observations of 7, 1, 1, 2, 2, 2, 2, 5. And in an experimental group, we also have 7 observations, which is 2, 3, 4, 4, 5, 5, 5. We don't introduce any other rules, so the program will just treat these numbers in their natural order, meaning 2 is more than 1, 3 is more than 2, 4 is more than 3, and 5 is more than 4. And important, we say these values can be considered independent observations. It's, for instance, not the case that it's the same subjects that in some kind of crossover design first do one condition and then the other. No, it's independent observations. It's no identical twins either that have been randomly allocated, one of the twin to the control and the other to the experimental group. We call these independent observations, no genetic or repeated measurements relations. Okay. Now we compare each value. So the prompt that we give to ChatGPT, the first is, so first we've given the data. So the data is here. These values can be considered independent observations, important. And then we basically give the following prompt to ChatGPT. Compare each value of the experimental group with each value of the control group. Each comparison should be calculated as the difference, experimental minus control, and the following questions should be answered. So what we're going to do is literally compare every observation in the experimental group with every observation in the control group, okay? So that gives, given that there are 7 observations in the control group and 7 in the experimental group, 7 times 7 comparisons is 49 comparisons all in all. We make these comparisons because this way we can calculate, which we will see later, the so-called relative effect, which is an effect size metric that comes among others with Brunner-Munzel's test. So, having given this prompt, we give a few questions. Question 1 being, what is the total sample size? So, if ChatGPT reads this information correctly, it should later tell us that the sample size is 14. Then, question 2, how many comparisons are there? So if ChatGPT does the right thing, it should tell us 49. And then questions 3, 4 and 5, they are about comparisons yielding a positive difference, number of comparisons yielding a negative difference. Negative would be that the control group has a higher score, because then experimental minus control would yield a negative difference. And well, there are also comparisons that are going to yield a 0 difference, and that will happen where the value of the experimental group is the same as the control group. For instance, if we were to compare the 2 of the experimental group with one of the 2s in the control group, well, so there are 4 comparisons here which give a tie, and well, later on with the 5s there is also a number of ties. So, okay, so those should be questions answered by ChatGPT later on. So, and then we say the relative effect numerator is the sum of the answer to question 3 and half of the sum of the answer to question 5, because what happens is that the ties we equally divide over positive and negative differences. And the relative effect denominator is the answer to question 2, the total number of comparisons. So, and then based on that information, we say question 6, what is the value of the relative effect? And then, okay, once that question is answered, for the relative effect, the number of successes equals the product of the answers to questions 1 and 6. Okay, question 7, knowing that, what is the number of successes for the relative effect? Once we have that, and we have the sample size as well, we tell ChatGPT for the relative effect, the number of failures equals the answer to question 1, which is the total sample size, minus the answer to question 7, which is the successes, because successes and failures together add the total sample size. Successes here will be the cases where experimental yields a higher score than control, plus half the ties. And the failures will be the other half of the ties and the negative differences. So that will be question 8. What's the number of failures? And then we go to the generalized relative effect, which is an effect size metric which follows the logic of the relative effect, but just treats it as a statistic that follows a so-called beta distribution. So we use that to do Bayesian proportion tests and add credible intervals around these point estimates. And then we say, suppose we add one success to the answer to question 7 and one failure to the answer to question 8, because we assume a default beta 1-1 prior. The default prior distribution for the generalized relative effect is a 1-1 beta distribution. And why I do that? Well, I explain in that paper. If that is of interest, I'm happy to provide the link to that article. It's an open access article, so you can see the logic plus a workout on how to do this GRE or generalized relative effect calculation procedure in R. Then questions 9 to 13, they pertain to the generalized relative effect. So okay, first of all, so we have already specified that GRE follows a beta distribution. We have specified the prior, and so given that we have the data, which is the questions to 7 and 8, so question 7 and 8, the number of successes and failures as calculated over the total sample size, so rescaled back from the number of comparisons to the total sample size. When we do that, we can ask, okay, so we get a posterior, so we have data, we have prior, so we get a posterior distribution. Every posterior distribution has also measures of central tendency. So here we can say what's the posterior mean of GRE and what's the posterior median of GRE. And well, usually the credible intervals are calculated around the posterior median. And well, okay, so some people advocate for a 95% credible interval, since that is most comparable with a 95% confidence interval. It's not the same, it will be slightly smaller, but it's more comparable to the 95% confidence interval than the other two. But while there are also scholars that advocate for a 90% or even 89% credible interval, because those tend to be a little bit more stable. So we just calculate all three credible intervals. Now note that in this entire prompt I have provided exactly 0 formulas, 0 calculations. All that I have done is provide descriptions of how you can get these statistics. So what I'm showing here in a second is that you can get a lot of calculations, a lot of outcomes without actually using calculations in ChatGPT, which is of course different from what it would be in R. No, if I use base R or some other package which is not a large language model, I would need to add formulas, right? So here I can just use text, a blurb of text, well, blurb of text carefully formulated, of course. And let's see what happens. So ChatGPT tells me, let's go step by step. Pairwise comparisons are asked, yes. Control group size 7, experimental group size 7. Hey, this is correct. All comparisons are experimental minus control for every experimental value against every control value. Perfect. So ChatGPT has correctly understood the assignment. Question 1 was, what's the total sample size? 7 and 7 equals 14, correct. Question 2, number of comparisons. Well, 7 values in the control times 7 values in the experimental, because we compare each value to each value. What is that? 49 comparisons, correct. Number of positive differences, 38. Number of negative differences, 4, and the number of zero differences is 7. This is telling me, which is correct, because the zero differences we can even calculate from the original data, because we have one experimental value which is 2 compared to, so 4 comparisons with control values 2. This will give 4 zero differences, and there is one 5 value in the control plus 3 5 values in the experimental group. So those would be the additional 3 zeros. So yes, correct. ChatGPT has seen that there are 7 zero differences or ties. There are 4 negative differences, which we could also do by hand, but I'll not do that for the purpose not to make this video too long. So the vast majority of comparisons is 38. Now, on the question on the relative effect, we said that the numerator is the sum of the positive differences, which is 38. That's the answer to question 3, plus half the sum of question 5. So that's why 38 plus a half times 7, which is 41.5, divided by what the numerator was, so the denominator, sorry, is the total number of comparisons. 7 times 7 equals 49. So we get a relative effect statistic of 0.84694. If you use an R package which calculates the relative effect as per Bronner-Munzel's test, or you do the same in Jamovi or some other package that program that has the option to calculate the relative effect, this is the number you get. I checked this number in R and it is indeed the same. All the numbers that I'm showing here, by the way, I tested in R. And on this number of decimals that they are provided, you get exactly the same in R, I can confirm. So question 7, which was question 7, well, the number of successes. What do we do? Well, we have the relative effect here, but what did we say? Well, of course, we don't calculate, because we are going to calculate successes and failures because later we want to get to that beta distribution. Of course, we cannot calculate the beta distribution based on the number of comparisons. That's 49. We don't have a sample size of 49, we have a sample size of 14. So one way to scale back is to say, okay, we have a total sample size of 14, we have a relative effect statistic of 0.84694. That gives a number of successes, which is just over 11.85. Well, and if we take 14 minus that 11.85 something, then we get 2.14 failures. Well, these are not whole numbers. Is that not a problem that we get decimal numbers of successes and failures? No, for the Bayesian proportion test, that is not a problem at all. Actually, it is very common to do that. So we get a we use a beta 1 prior, which we said, now that is here, assume a beta 1 prior. So we add one success and one failure. So posterior alpha, which is the posterior number of successes, is the data successes, which is 11.857 plus 1. And we do the same for the failures, 2.14 and a bit plus 1. So we get a generalized relative effect beta distribution with just over 12.85 successes and just over 3.14 failures. And when we do that, we can calculate the posterior mean of the generalized relative effect, which is just alpha divided by alpha plus beta, which is just over 0.8. And when we calculate the posterior median, which is the 50th percentile of the posterior distribution, which is 0.816. Again, if you do these numbers in base R or in some other packages that allow you to calculate the posterior median, you will get this number. And then we wanted some credible intervals around that point estimate, and we get as a 95% credible interval 0.584 until 0.952. The 90 and the 89% interval, of course, are a bit narrower because, well, the smaller interval, the smaller the percentages, it includes less of the distribution, so it gets a bit more narrow. Okay, but in any case, regardless of whether we use the 95, the 90 or the 89% credible interval, these intervals entirely exceed the 0.5 value, which would be the value of no difference between conditions. So we would say that we have evidence of a positive, evidence of a positive treatment effect. And well, in the paper that I recently published on the GRE, I argue that values around 0.55 0.56 and 0.55, 65 and 75 are associated with small, medium and large differences. So this interval also lies entirely above 0.55, for instance. So if there was a region of practical equivalence where we say, well, as long as we find values between 0.45 and 0.55, which would be like small deviations, then we don't have enough evidence against practical equivalence. But in this case, we would say, well, this interval exceeds the 0.55 value as well. So you would even be able to say that we have sufficient evidence against that region of practical equivalence. So yeah, and then what actually, if you see here, if you want, I can also show the full comparison table or reproduce this using R. You cannot see this in the let's see if I can, yeah, you see, if I just drag this up a little bit, now you can see, if you want, I can show the full comparison table or reproduce this using R. This is interesting, and I will say to this, yes, the full comparison table. So now it will probably provide me with a matrix. That is exactly what happens. This is actually what should be done here. So you see that, yeah, this is a 7 by 7 matrix. There is another video which I have on my YouTube channel where I give such a matrix, actually using Excel, because you could get this matrix. This is easy to calculate in Excel as well. And so here you see literally on the left the experimental group, here up it's the control. So 2 for the experimental minus 1 for control, that's a difference of 1, so it's a positive difference. Now the absolute values may not mean much, because for the relative effect and also the generalized relative effect, we don't use the magnitude of differences, but we just say positive, tie, or negative. What's the rationale behind that? Well, these are non-parametric statistics, and if we because okay, we say we have values 1 to 5, but in order to use parametric procedures, like for instance the t-test, we want to assume first of all that the measurements 1 to 5, that those are of interval level of measurement, meaning that the difference between 1, 2 is the same as the difference between 2 and 3, etc. So each consecutive number has the same distance to the previous and to the next, which we don't know if these are, for instance, ordinal ratings, meaning like, for instance, 1 poor, 2 borderline, 3 satisfactory, 4 good, and 5 excellent. Well, we don't know if the difference between 5 and 4 is the same as between 4 and 3, for instance. So that's ordinal ratings. And with this kind of non-parametric procedures, you respect that ordinal nature, which is not what you would do in a t-test. You would just say, nah, all distances are the same. And besides, you would want to also assume some kind of, you make distributional assumptions. You would, for instance, in the ideal case of a t-test, you would say that, well, these observations that we have for the control group and the experimental group, these observations, they are samples, random samples from normally distributed populations. Those are assumptions that are difficult to check with small samples, and while in the control group, for instance, we have 6 of the 7 values which are towards the lower end of the scale, and then we have a 5 observation here, which is very far away from the rest. This could be an outlier. This could be maybe the distribution in that population is something else than normal, is bimodal, something we don't know. But in any case, we don't. I mean, I would not treat this set of 7 observations as a sample from a normally distributed population. I would not want to make that assumption. Yet it is critical because in the end you want the sampling distribution for your t-test to be normally distributed or approximately normally distributed. That can only happen when either the population that you draw from, and the populations here for control and experimental, are normally distributed, or the samples are large. Well, 2 times 7 doesn't constitute usually like a large sample to get an approximately normal sampling distribution if the populations are very skewed, for instance, or there is bimodality. So I don't want to make that kind of assumptions that come with the t-test. Another one, you might wonder, okay, do you assume equal variances or unequal variances? Again, difficult to test with these samples. I don't want to rely on such assumptions, and any tests for normality or equal variances would probably lack power anyway to detect differences. So we just go non-parametric. And that's why we talk about, okay, although this matrix, of course, lists the absolute differences, anything above 0 will count as a positive difference. Any 0 will be counted as a tie, and any negative difference, which we also have here, where the value in the control group is 5, and in the others it's lower. So yes, there are exactly 4 values which are for comparisons which yield negative differences, so that would be in favor of the control group. And you also see 1, 2, 3, 4, 5, 6, 7 zeros, so that's also correct. Yeah, but the answer that was given before, 7 ties, is correct. So yeah, here you see this is an example of how you can get these outcomes in ChatGPT using words, like language prompts instead of formulas. One thing where I would place a bit of a note of caution is, so it tends to say here recreated in R, Python, etc. Okay, or Excel format. This matrix, for instance, is already in Excel format. But when it says recreated in R or Python, I would be a bit careful. Always test it. I mean, in any case, when you develop a language prompt for something like this, or for a parametric statistic, always cross-check it with a known package, either a package in R or a Jamovi or Stata, or a program that is known to provide the correct solution. Before you just blindly trust on ChatGPT, because as I showed in another video, ChatGPT can, and it also says that here below, ChatGPT can make mistakes, and I can confirm that for statistics that is the case. Correlation calculations can be wrong, and even when it says I got this from R, or this is the R code, I can tell you that it is still sometimes hallucinates or invents code, which if you were to actually use it in R, it will not run, because some of the like the small, even if it's just a small part of the code, but some of the parts will not be exactly as you should do it in R, and so you will not get the outcomes, or you will get something incorrect. Anyway, I thought I should share this. I will probably be developing a few more videos on this kind of content, because people have asked about it. Like, yeah, is it possible to do statistics, with programs like ChatGPT? I mean, my correlation video that I did a while ago was already an answer, at least in the sense of be cautious, always test with known programs. But I will be adding more content. Now, one final note that I should make, of course, if you are an R user like myself, or a Python user, then you will have code for something like this, which you can just reproduce for different problems, and it will run in seconds. If you use programs like ChatGPT, it will take a little bit longer. I don't have the log here for how much time it took me to actually run this whole prompt. I think it was about a minute. And well, the matrix went pretty fast, but I did the same prompt in a version of DeepSeek last week, and DeepSeek told me that it had to think 247 seconds, which is about 4 minutes. So it runs more slowly than R or Python. But well, if you are not an R user or a Python user, you don't know how to program, and you don't have immediate access to other statistical programs either. Well, maybe there is a way to get the outcome. But still, double check with a program once you can. Okay, thank you for watching, thank you for listening, and well, maybe see you in the next video. Have a good day.